Our paper is Trap-Aware MPC, an online controller algorithm for handling novel environments with unforeseen traps. Intuitively, traps are states in which the robot gets stuck. For example, object manipulation in clutter could encounter frictional jamming between the object and other objects or the walls. Or in the case of peg and hole, with unmodeled obstructions around the goal, where the traditional strategy of sliding the peg around will get stuck against them. More formally, traps are special states that are the product of the environment and a given controller under which the robot will remain in these states once entered. For example, in this planar pushing problem where the block frictionally jams against the wall, there are no actions that immediately decrease the distance to the goal below it. If the robot could see its surroundings, for example with visual sensing, and knew the effect of walls on the dynamics, then a planner could be used to set intermediate waypoints as shown. However, we considered the much harder problem where we cannot sense future traps, in this case being limited to sensing reaction forces. Additionally, we do not have any traps in our training data. The point is to enable our robot to online adapt to a wide variety of environments with different and novel types of traps. To that end, our method is made up of two components: offline representation learning and online control. Our representation generalizes out of distribution by inferring inherent invariances in the nominal training data. Our controller is a two-level controller where the high-level controller outputs the dynamics model and cost function that the lower-level MPC uses to compute action. Our controller explicitly reasons about non-nominal dynamics and traps and balances exploiting the dynamics towards the goal and executing recovery policies to escape traps. In all cases, nominal environment refers to free space. Again, we emphasize that there are no obstacles in the training data. We collect nominal data by sampling uniformly random actions in random initial conditions around the origin. Let's look at side-by-side comparisons of our method against baselines on planar pushing and peg and hole tasks with traps. Top left is our method. See the paper for more details on the baselines. We first focus on our method. It alternates between exploiting dynamics towards the goal and escaping traps by executing an adaptive recovery policy. Previous traps are remembered and labeled as bread poses with the corresponding action taken in that transition. These regularize the goal-directed cost during exploitation to avoid re-entering traps. At this point, the baselines are stuck in traps. SAC coincidentally output actions that keep the block parallel to the wall for out-of-distribution reaction forces on this task. SAC and the virtual obstacle baseline no longer make progress because the goal is behind the block, requiring a U-turn, which is a long action sequence that temporarily increases cost. Under these controllers, this is a trap. Our method continues down the hall while periodically entering new traps. These are unavoidable because we cannot anticipate them given limited sensing. On the peg tasks, our trap set is critical for avoiding previously seen traps. One challenge of this task is that the goal is next to a trap. The repulsion from the trap set and the attraction of the goal induces a potential field that could have many local minima. To address this, we anneal the trap set weight when in nominal dynamics. Note that most of the parameters use the same value across environments and tasks, demonstrating the robustness of our method. See the paper for how to independently tune some parameters to improve performance. Here we consider a very out-of-distribution translative version of PEG-T. Thanks to our generalized representation, which learns to be invariant to translation, our method and the APF baselines still perform well. In summary, our method combines a learned representation that generalizes our nominal dynamics and a hierarchical controller that explicitly reasons about non-nominal dynamics and traps to escape unforeseen traps in novel environments. For all tasks, our method achieves at least 60% success, while some of these are hard such that trap handling baselines achieve less than 50% success, while our other baselines never succeed.